Hello, my name is Charlie Zoller, and I'm a first-year graduate student at University of Illinois, Chicago. My advisors at the moment are Russell Hemley and Mukhtar Haiti, and I've been in collaboration with Sergei Tkachev and Vitaly Prokopenko of APS's Jessicar's facility and Sakun Duwal of Sandia National Laboratory. Our lab is currently engaged in a massive collaborative effort with Sandia National Laboratories and affiliate labs to compile a broad and robust equation of state of hydrogen-helium mixtures across magnitudes of pressures and temperatures. Measured with Sandia's Z machine, its titanic energy and compression can bring the samples to millions of degrees Kelvin and tens to 100 megabars of pressure. Our program is completing just one piece of this grand experiment. We are measuring the pre-compression data in order to wholly understand the mixture's density-pressure equation of state prior to loading in the Z machine. A full understanding of the most basic elemental makeup of our universe gives a better understanding of binary fluids, the evolution of gas giant planets, and the properties of these mixtures at stellar conditions using the Z machine's power of fusion. Brilliant spectroscopy has been a primary tool for the calculation of the density equation of state of these mixtures. Brilliant spectroscopy is a technique similar to Raman spectroscopy in that it measures the inelastic energy change of scattering photons in a sample. Here, we are measuring the incoming photon's interaction with acoustic phonons, which are directly related to the speed of sound in a material. During this scattering process, an energetic phonon will release energy, or a lower energy phonon will get energy with the interaction of these phonons. This change in outgoing photon energy will correspond to the primary peaks seen in this graph. These are known as the Stokes and anti-Stokes lines. The peaks of these correspond directly with the speed of sound, which the equation is given in equation 1. Given the velocity, the density may be calculated through integration, seen in equation 2. We will need the initial density of our sample, which may be calculated using optical measurements talked about later, calculating volume changes by pressure, which will give the initial density at a given pressure value. The results from 2 runs of equal ratio hydrogen to helium mixtures are quite consistent with one another. The most recent run indicates a very strong correlation with an ideal ratio hydrogen-helium velocity calculated with the equation 4. The slight decrease in velocity seen with Dr. Duwal's data may indicate a slight hydrogen diffusion from the cell prior to measurement, thus producing a more helium-rich velocity profile. Volume measurements were performed by capturing a 10 times magnified image of the gasket hole, as well as calculating the change in height after an increase of pressure using calipers. The area was calculated through an appropriate photo editing software. Unfortunately, there is a smaller data set than desired for the first run. The overall trend is consistent with very high compressibility of fluid hydrogen-helium, however. We also calculated the index of refraction using our Raman system as well as a monochromatic light, which gives us fringes. We use this to calculate the index of refraction as well as compare against previous measurements of the thickness of the gasket hole. Going forward, we are planning on testing multiple ratios of hydrogen-helium mixtures over the same pressure range. We'll be using the same Brilliant and optical techniques described earlier. Hopefully, we will also vary temperature of some of these compositions to get a much more complete pressure, volume, temperature equation of state.